First of all, and I'd like to thank the organizer for having given me the opportunity to talk today and to present, in some sense, the analytical part of my PhD thesis that was done in with the supervision of Stéphane Menozzi from the Paris-Saclay University and in co-supervision with Enrico Priola from the University of Pavia. So my talk today will focus on Schauder estimates for 3 different classes of degenerate no-local evolution equation. So in some sense, this kind of estimates are a very useful analytical tool because, for example, they are often linked with the well-posedness of the associated stochastic differential equation. And in some sense, it was our first main motivation for this kind of study was essentially linked with the this kind of analysis for the regularization by degenerate noise phenomena. So in order to fix, sometimes present this kind of degenerate equation in the clearest way possible, I will start with a toy model. In particular, if we fix some finite final time big T, a source F, and a final condition U of T, in some sense, what we will see as the bigger state space R to the power n times D, we are essentially interested in studying this kind of Cauchy problem involving a Ornstein-Uhlenbeck operator, where the main part is the generator of an alpha stable process on a smaller space R to the power of D. So it is in this sense we are talking about the degenerate operator. Okay, no problem. So so we say that this kind of operator is degenerate in the sense that it acts only on the first, let's say, macro component. So which are the kind of classical assumption for this kind of degenerate problem? As said before, we say that the operator is an alpha stable one in the sense that its Levy measure is decomposed into a radial part that takes into account the stability index alpha and a spherical measure, usually called the spectral measure, that we assume to be symmetric and to satisfy the following non-degeneracy assumption. Roughly speaking, we essentially impose that the Levy symbol that is associated with our operator is comparable up to some multiplicative constants with the Levy symbol of the classical fractional Laplacian. I would like now to essentially point out that this kind of assumption is clearly satisfied by the uniform measure on the sphere that corresponds to the classical fractional Laplacian, but also by very singular spectral measures, such as, for example, the sum of Dirac masses along the axis that instead correspond to the so-called pure cylindrical fractional Laplacian. Moreover, this kind of assumption intuitively provides the operator with a smoothing effect of order alpha that, however, apply only on the first component of the system, indeed because this kind of operator is degenerate and acts only on the first component. In order, in some sense, to obtain the transmission of this kind of regularizing effect into all the system, we'll then need this kind of Ormander-like condition on the system for the hypoellipticity of the system. More precisely, we will assume this kind of minimal structure for the matrix, in the sense we assume that only the elements of the subdiagonal of the matrix are non-degenerate, and that essentially allow this transmission into all the system for this kind of smoothing effect, and elsewhere they are 0. So before stating our Schauder estimate, our main results for this kind of in this kind of section, we first need to understand which is essentially the most suitable functional space in which to state this kind of estimates. And to do so, we first need to analyze the intrinsic geometry of the system. More precisely, since inspired by the works of Lanconelli and Polidoro, the point is to look at the dilation operator for the system that is invariant into for our degenerate system, in the sense that it transforms solution of the equation into other solution of the same one. If now we take into account the classic alpha scaling for the alpha stable operator, but again only with respect to the first variable, and we then add the transmission into all the other variables, their direction, thanks to these non-degenerate subdiagonal elements, it's not difficult to check that the wanted dilation operator has the following exponents. And then we can so introduce, as a suitable functional space, a older space with multi-index of regularity. The point is, in some sense, the associated semi-norm is gives a uniform, homogeneous property in terms of the dilation. In particular, this kind of anisotropic older space can be calculated, can be understood component-wise, in the sense if we fix one direction, I, for example, we can calculate the classical older semi-norm along that direction and uniformly with respect to the other variables. But however, with older index, it is scaled according to the dilation operator exponent along that direction. And we can then sum all the contribution altogether. Moreover, this is particular for future reference. We'll also, consider the actual norm, where we consider in addition the supremum norm. So I can here essentially state the kind of result we'll see also in the next frameworks. If we assume that the source and the final condition are in the expected anisotropic older spaces, expected in terms of the, in some sense, bootstrap we can obtain from this kind of evolution equation, we can show that there exists a unique solution for the problem and that the Schauder estimate holds. However, we need, in particular, to assume this kind of constraints on the indexes alpha and beta that, in some sense, can reflect, at least heuristically, the fact that we are considering possibly non-isotropic alpha stable densities. So, which are the main point, the main ideas for this kind of to obtain this kind of results? In this linear framework, it is well known that variation of constant formula allows to represent the solution of the problem in terms of the semigroup. And then the main point is to understand the behavior of this kind of semigroup with respect to the anisotropic older spaces we have just defined. To do so, we firstly move to the stochastic framework, to the stochastic counterpart, in the sense that the process X is the Ornstein-Uhlenbeck process, where the driving process Z is the alpha stable process whose generator is given by our operator curly L of alpha. And we can then, through a precise analysis of the Levy symbols of the object, in the involved object here, we can show that actually the stochastic convolution can be seen, at least in law, as a alpha stable process, again symmetric, again non-degenerate, but now on the bigger space, the bigger state space R to the power of ND. However, again, in some sense, due to this kind of anisotropic nature of our system, we need to rescale it according to this kind of intrinsic time scale matrix M of T. Thanks to this identity law and the fact that the process S is non-degenerate, we then know that there exists a smooth density, and we have then a good representation of this kind of density. Now we can, now that we have a good, we can rely on this density, we can actually try to control this semigroup in terms of these anisotropic Hölder spaces. To do essentially here, two different and opposite patterns appear. On one end, we have been able to show that the derivatives of this density can be controlled by another density with, again, suitable properties, but at the price of additional singularities in times we will have then to control, where, again, the exponents are in some sense coherent with the dilation operator for the degenerate system. In order to recover, at least in part, this kind of time singularities, we then rely on this anisotropic smoothing effect that is associated with the degenerate semigroup. In particular, balancing precisely these two different behaviors, we can finally show some suitable a priori control for the semigroup as a linear operator between these anisotropic Hölder spaces. And then from using this kind of estimates, not difficult to show that the Schauder estimates indeed hold. So as a second framework, sometimes one can ask himself if it is actually possible to consider a more general class of Levy operator. More precisely, if we consider again the same kind of Ornstein-Uhlenbeck operator, where now, however, the main part, curly L, is a more general Levy process, again on the smaller space R to the power of D, that we recall is given by its Gaussian term, is a linear term and its Levy measure. And if we consider again the same kind of Ormander-like condition, the same kind of subdiagonal structure for the matrix A, we, however, consider a more general non-degeneracy assumption here, usually called of stable domination, that heuristically say that the Levy measure of our Levy operator is bounded from below with the Levy measure of a truncated alpha stable, of the Levy measure of a possibly truncated alpha stable operator. This kind of assumption allows us to consider a more general class of stable type operator, not only the classical stable operator, but also the relativistic or the layered or the tempered stable operators. And importantly, we do not need anymore to assume the symmetry of the Levy measure, and neither the constraint on the indexes alpha and beta. Again, this was shown in my work in 2021 at the Journal of Mathematical Analysis, that even for this more general framework, it is possible to obtain the same kind of results. There exists a unique solution, and the Schauder estimates holds. More precisely, actually, in this work, we were considering more general version of time-dependent matrices under the so-called Kalman-Rank condition, and we consider there also the elliptic problem, but the main elements are essentially the same. So, which are the main idea of the proof of this kind of results? Again, in this linear framework, the point is to consider to establish suitable a priori control on the associated semigroup for the Ornstein-Uhlenbeck operator. Again, with a slightly more complicated analysis, by some sense similar, we can show the same kind of identity in law for the Ornstein-Uhlenbeck process, where, however, here the process S is a more general Levy process on the bigger space R to the power of n d, that satisfies again this kind of stable domination property. In particular, for future reference, I will write with the tilde elements the Levy triplet for the process, and I'm going to write the truncated alpha, Levy measure of the truncated alpha stable operator by curly ni of alpha. Thanks to this identity law, we can then obtain a first representation of the semigroup in terms of the law of this Levy process S of t. Now, in order to obtain a suitable control on P of t, we actually need to understand better the behavior of this kind of law. In particular, inspired by a work of Schilling, Zotionik, and Wong in 2012, the point is at least formally to decompose the Lévy triplet of the Lévy process S of t in a good part that's essentially associated with the small jumps of a Lévy process and the remainder term. And exactly thanks to this kind of stable domination property, we can then associate, in particular with the remainder term, the associated probability measure, and in this way obtain a suitable decomposition of the law of this process S of t. In particular, since this law is associated with the small jumps of an alpha stable process, we know that admits a density with suitable properties. We do not need to consider, again, this kind of constraint, because here we do not consider the heavy tails of the Lévy process, since we consider only the small jumps. And this kind of final representation for the semigroups gives us the idea on how to conclude, again, this kind of Schauder estimates. The point is to rely on the good variable, y1, that is associated with the good density for the truncated, for the small jumps of the alpha stable process, and apply in some sense the same kind of techniques we have seen in the first framework, but only with respect to the good variable. While on the other end, the sometimes tricky part is to be able to control the remainder term, the bad variable associated with y2. Again, we can obtain for this kind of partially technique the same kind of controls for the semigroup, and with them it's not difficult to obtain again the Schauder estimates. To conclude, one of another natural question one can ask himself is, it's possible now to consider a more general operator with nonlinear drift. More precisely, we are interested in this kind of Kolmogorov equation, where now the main part is again this kind of alpha stable operator we have seen in the first framework, and where this nonlinear drift has this particular upper triangular structure that heuristically, in some sense, is an analog to the subdiagonal structure of the matrix A in the H&ouml case, and in some sense allow to, we have to be sure to not distract this kind of transmission effect we need. This is fundamental for this kind of degenerate framework. We'll then need some regularity assumption of this nonlinear drift. In particular, we'll assume there's a parallel properties of this subdiagonal structure. In the sense, we assume that the subdiagonal elements of the Jacobian are non-degenerate, and we assume this kind of in all the regularity of increasing order in I for the drift. Importantly, however, we do not assume, we assume that it is all the regular, but it may be unbounded. So again, if we under some additional constraint on the indexes alpha and beta, in particular for this kind of nonlinear, drift, we can only consider the subcritical case, so alpha is greater than 1. I've been able to show in the Bulletin of Science Mathématique that again there exists a unique solution in a weak sense, and that the Schauder estimates holds. So to show this kind of results, the point was to adapt the perturbative approach with forward parametrics expansion that was firstly used by Schauder et al., Honoré and Menozzi for the diffusive settings, and that is essentially rely on the choice of a suitable proxy operator, that is an operator that is not too far away from the original one, but has some suitable, more well-known, at least, properties. So, more precisely, inspired by the work of Krylov and Priola of 2010, we need to, depending on some freezing parameter, we will have to choose carefully at the end. We choose a flow that is the solution of the dynamics involving the nonlinear drift himself. And we can then introduce, essentially we can linearize the nonlinear drift along this flow. And here you can see that actually this kind of time-dependent matrix has the exactly same structure of the Ornstein-Uhlenbeck matrix A. And we can then choose as the suitable proxy the operator obtained from the original one by switching the nonlinear drift with the linearized one. In particular, noticing that this kind of object is essentially a time-dependent Ornstein-Uhlenbeck operator, we already know from the first framework that this the associated corresponding semigroup has some suitable smoothing effect, some suitable control. Moving to the actual perturbative approach, the point is at least formally to rewrite the equation of interest in terms of the proxy operator, and then using a kind of duhamel type expansion formula to write any solution of the problem in terms of the frozen semigroup and the remainder term that essentially is given by the error of the approximation of our nonlinear drift. Then, since we already know some suitable properties for the frozen semigroup, essentially what it remains to be done is to control this kind of remainder term. So here, in order to control the error, the arguments are a bit more technical and involved, but the point is essentially to decompose it in two parts. On one end, we have, with respect to the first variable, non-degenerate 1, we expect the solution u to be differentiable with respect to the first variable, because as I recall, the solution u is assumed to be in the Hölder space of order alpha plus beta, with alpha is bigger than 1, while on the other end, for the degenerate components, we need a much more technical, much more complicated reasoning in terms of Besov duality, Besov norms, essentially in order to extract all the minimal regularity we have in order to deal with the controls of this kind of object here. So in order to conclude, I will only like to give some intuition, since our aim was to establish this kind of Schauder estimates under the minimal Hölder regularity for the coefficients, why in some sense we need this kind of increase in regularity, Hölder regularity for the drift. In particular, if we denote for the moment by beta ji the regularity of the ith component of the drift with respect to the jth variable, and we recall that beta can be as small as we want, this kind of regularity assumption can be translated into requiring that this kind of thresholds hold for these beta ji indexes. If we then look at the some sense typical computation for this kind of estimates, that is to obtain an integrable singularity in time for this kind of object, this kind of term that was, for example, appearing before in the control of the remainder term, and we look at the exponents for this kind of the exponents of the time singularities for this kind of object, at, for example, at the jth level, at the jth variable, we recall that the derivative of the density gives this kind of exponent, while we can use the Hölder regularity of the ith component with respect to the jth variable that is given by beta ji, but rescaled accordingly again to this kind of link between time and space and with the dilation operator. In particular, if we want that to be integrable, we essentially obtain, in some sense, heuristic way, this kind of thresholds. And in some sense, what it means is that in order for our work, our method to work, this is essentially the minimal regularity we need for the nonlinear drift for everything to actually work. So to conclude, I would like to give some references. So here are some of the articles, some works I have mentioned at some point during my talk. While here are some more general references about Schauder estimates for this kind of degenerate framework. In particular, here is the same kind of results has been obtained in the diffusive local case for the nonlinear drift. This is essentially at least to best my knowledge, the only other article that works with degenerate alpha stable operator, even if here they only consider the kinetic case, so that they have only two components, and they use a slightly different approach through anisotropic Littlewood-Paley decomposition of the space. And here are some more sometimes well-known results for Schauder estimates in the for Ornstein-Uhlenbeck or Ornstein-Uhlenbeck with some additional nonlinear drift along the good variables in some sense. So thank you very much for your attention.
Okay, it is time for some questions and remarks. Do you have? Probably we have in chat. No? Oh, okay.
Thank you very much for the talk. I was wondering, like, when you started to do research on this problem, I mean, did you get the equation as it is now on the slides with some, let's say, physical motivation behind some discrete approximation of it from, I don't know, some model, etc. And I immediately do a second question for later, like if you have some results on domains that are not just, I mean, some bounded domains, let's say.
Okay, now for the first about some kind of physical motivation, in some sense we were starting indeed from some sense stochastic framework. So this was a step in order to establish the well-posedness of the corresponding degenerate stochastic equation that has, however, a lot of connection, in particular with kinetic equation, so that when we consider, for example, this kind of models only when we have only two components, but however, for the more, in some sense, general chain of equation, at least from the stochastic framework, they can be linked, for example, in finance for sure, with this kind of the behavior of this kind of Asian options, again in kinetic equations, and for the more general chain for this kind of models for earthquake diffusions of the process when this, okay, this is much easier in the local Brownian settings. For the more general fractional one, we then need, so for example, for the earthquake model to have some different density of the materials, for example. So we have this kind of actually jump for the problem. And the second question about the bounded domain, actually no, because in some sense the problem is that this kind of, the geometry for this kind of object is really, really strict, in the sense that if you just slightly change a little, you ruin this kind of transmission. The regularization effect doesn't arrive to the, in some sense, lower direction of the system. And then it's really much, much more complicated and almost impossible to show that we have this kind of smoothing effect of all the object. So maybe, yeah, it's probably can be possible while you need to choose, in some sense, the bounded domain in a proper way in some very specific model, probably.
Okay, thank you.
Oh, thank you.
Thank you. Okay, thank you very much. Now, if we do not have